This lesson deals with Supplemental Problem 511, Sequential Switching. You can find this in the course ebook in the Chapter 5 Supplemental Problem starting on page 15. Sequential switching is whenever switching occurs more than once in a circuit. So here I have an example with one voltage source, 5 resistors, 1 inductor, but 2 switches. Now since we have only one inductor, this is a first order differential equation. We're going to solve for the current through and the voltage across the coil. Now for t less than 0, both switches are closed, and then as t passes through 0, switch 1 opens up. We really have an example just like we had in the past with a one switch problem. We'll take a look at this 35 millisecond switching in a little bit. So we can use our 6-step algorithm to analyze this first switch action. On step 1, we're going to formulate the equations. These equations will be valid for t up to 35 milliseconds. The current of the inductor and the voltage across the inductor will be the form of sum a plus b times e to the minus t0 over tau. Since t is switching at 0, we'll just have e to the minus t. We'll call this one a1 and b1, a2 and b2. And they both have the same value of tau. In fact, any voltage or current you solve for would have the same tau in its equation. Step 2 is to find the pre-switching conditions. Since we have these two variables, we're going to solve for the inductor current at 0 minus and the voltage across the inductor at 0 minus. Now minimally we have to have the current because this doesn't jump instantaneously. We're going to use that to solve for our constants a and b. But t equals 0 minus, both switches are closed. We assume that this inductor has been in the circuit a long time, so it looks like a short circuit, that the current isn't changing, and so we have V is equal to L di dt, and that'll be equal to 0. And so that's my beginning. Now that voltage of 0 is across this resistor, so there's also no voltage across here. And that means there's no current flowing in here. So the current in the inductor is also the current in the 3 ohm resistor. If I could find the voltage across this 3 ohm resistor, I could find the current. Now with a short circuit here, I have the 3 ohm in parallel with the 6 ohm in parallel with the 12 ohm. I can find the voltage V, which is also the voltage over here because of the short circuit, by using a voltage divider. 12 in parallel with 6 in parallel with 3, voltage divided with 4 ohms and 60 volts. That turns out to be 18 volts. There's 18 volts across here. The current then is 18 divided by 3, or 6 amps, and that 6 amps flows into the inductor because nothing goes over here. In step 3 of our algorithm, we're going to find the initial conditions. And this would be the voltage across the inductor and the current through the inductor at t equals 0 plus. T equals 0 plus, this switch becomes an open circuit. But this one is still closed. Now the current that was flowing in this inductor before the switch opened here was equal to 6 amps. And that's the value at 0 minus. But that has to be the same as 0 plus because we can't have an instantaneous jump in current because V is equal to L di dt, and that would produce an infinite voltage. That value of 6 amps is going to be equal to A1 plus B1 times e to the 0, or just A1 plus B1. Now the voltage across this inductor we'll have to solve for by using the resistors in the circuit. This switch open, I've got this 6 and 3 in series, and that's in parallel with 18. You can think of this as just one resistor here by combining the 18 with the 9, and that'd be the product over the sum. That turns out to be 6. And this current is going to flow in this direction and create a drop this way. Going to be a negative 6 amps times that parallel combination. That turns out to be minus 36. That's going to be equal to A2 plus B2 times e to the minus 0, or just A2 plus B2. Step 4 in our algorithm is to find the final conditions, and that's let t approach infinity. But at 35 milliseconds, this switch is going to open. The circuit is following the solution of the differential equation prior to that, and it really doesn't know that we're going to open or close the switch or do anything in the future. So we could pretend that this switch isn't going to open, and simply use our algorithm and let t approach infinity and solve for another set of data points so we can solve for our a's and b's. So I'm going to write down here, let's let t approach infinity, but put quotes around it to indicate the fact that we're using this as a mathematical technique and that we're going to find our unknowns and then go back and deal with the switch opening at 35 milliseconds. If the switch were to stay closed, then what's going to happen? Well, the inductor, if you wait long enough, will look like a short circuit, and that means the voltage across it is 0. So what's the voltage across these two resistors? Well, they're also 0. One simple way to argue that is just do a voltage divider. The voltage here would be 6 ohms over 6 plus 3 times 0, and the voltage here would be 3 over 6 plus 3 times 0, or just 0. Now the 0 volts here also implies that this is 0 volts, which makes the current in here 0, and it also makes the current in here 0. This current here is going to be equal to minus 0, or just equal to 0. So the voltage 0, because it's a short circuit, that's going to be some A2 plus B2 times e to the minus infinity with quotes around it, or just A2. And this one's going to be A1 plus B1 times e to the minus infinity with quotes around it, or just A1. Now, a fifth step in our algorithm would be then to look back from the inductor with the switches in their states. So again, we're thinking of this still as not changing state. And looking back at here, we see 9 ohms in parallel with 18, but we found that to be 6 ohms before. Time constant is going to be L over R Thevenin. It's going to be 150 millihenries over 6 ohms. That's 25 milliseconds. Now we can complete step 6 of our algorithm, which is to solve for our constants A and B. We had A1 plus B1 was 6, A1 was 0. That means that B1 is equal to 6. So I of L of t is going to be equal to 0 plus 6 times e to the minus t over tau 1 of 25 milliseconds. When t was less than 0, we found that it was 6 amps. I'll include the equal sign here because the current cannot jump instantaneously as we pass through 0. For the voltage, we had that A2 plus B2 is equal to minus 36. A2 was 0, so B2 is minus 36. B sub L is equal to 0 minus 36 times e to the minus t over tau. Okay, I'll call this tau 1 due to our first circuit. And this will be valid between 0 and 35 milliseconds because the voltage can jump instantaneously. In fact, it did. We jumped from 0 volts to minus 36 volts. So that's our result like we did previously. We did our 6 steps and we found the results of this circuit. We did assume that the second switch was not going to change state so that we could solve for our constants. But it is going to change state, and this is what the circuit's following in terms of a solution. So now what happens when we pass through 35 milliseconds? Well, that second switch opens, and again, we have a circuit that has resistors, an inductor, and a switch. Our voltage source is actually disconnected. We'll have a first-order differential equation solution for the inductor current and the inductor voltage in terms of some A plus B times e to the minus T0 over, say, tau 2 now for our second condition. Here, T0 is equal to 35 milliseconds. And we use a subscript 3 and 4 here because these A's and B's are not the same value. We're basically going to repeat the 6-step algorithm again, where step 7 is really our step 1. So we'll find the pre-switching conditions. Now here's something a little different. We would normally assume that the inductor's been in the circuit a long time and we treat it like a short circuit. But that's not the case. It's actually following these equations. Just before we switch, we could evaluate these equations and figure out the value of the inductor current and the inductor voltage. The inductor current cannot jump instantaneously. The voltage can. Plug in the value of 35 milliseconds into the first equation. That turns out to be 1.48 amps. In the second equation, it turns out to be equal to minus 8.88 volts. So that's a little bit different in this multiple switching circuit. Is that we're going to use the equations from our first 6 steps to figure out the pre-switching conditions. What are the initial conditions? Now, as we pass through 35 milliseconds, just after that, this switch opens, but the current that was flowing in the inductor is also flowing in this resistor, and that's still 1.48 amps. That's going to be equal to my A3 plus B3 times e to the t minus T0. Now, t is 35 milliseconds, and we're subtracting T0, so we again get e to the 0. We just have 1 times B3. We have A3 plus B3 is 1.48 amps. For the voltage, I've got this current flowing through these two elements. It's going to create a drop in this direction of 9 ohms times 1.48 amps. That's going to be, with respect to this polarity, a minus, in this case, 13.32. Again, it's going to be equal to some A4 plus B4, e to the minus 0 over tau 2, or just A4 plus B4. Our next step, 10, is the same as step 4. We'll take a look at the final conditions as t approaches infinity. But this time we can do that because we have no more switching in our circuit. The switch is open after 35 milliseconds. This inductor has been in the circuit a long time, so it looks like a short circuit. That's equal to 0 volts, and that's going to be equal to A4 plus B times e to the minus infinity, which is just 0 times B4, so that would just be A4. There's no current in the open circuit. There's no voltage here, and so there's therefore no voltage across here, and therefore this current is also equal to 0. That's going to be equal to A3 plus B3 times e to the minus infinity, or just A3. Our next step would be step 11. That's finding the Thevenin resistance seen by the inductor for t greater than 35 milliseconds. So we have our first switch open some time ago. Here's our second switch open. Now looking back, we just see 9 ohms. L, which is 150 millihenries, divided by 9 is 16.67 milliseconds. So now we can do our step 12, which is again our 6th step done twice. We found that A3 plus B3 was 1.48. A3 was 0, so B3 is equal to 1.48. I sub L of t is going to be equal to 0 plus 1.48 times e to the minus t0, which is 35 milliseconds, divided by tau 2, which was 16.67 milliseconds. And the units here are amps. We're going to have equality because the current cannot jump instantaneously. For the voltage, we had A4 plus B4 was minus 13.2. A4 was 0, so therefore B4 is minus 13.32. Voltage is equal to 0 minus 13.32 times e to the minus quantity t minus t0, 35 milliseconds, divided by 16.67 milliseconds. Don't have the equality here because we are going to see a jump in voltage. It doesn't have to jump, but in this case it did. Sketch that. So we saw that when t was less than 0, the current in the inductor was 6 amps, and then we had a first time constant, so we started to decay, and when we got to 35 milliseconds, we were at 1.48 amps, and now with our second equation, we'll eventually go back to 0. It'll take about 5 time constants, so 5 times 16.67 is about 83 milliseconds. So we'll come back to 0. The voltage across the inductor started out at 0, it jumped to minus 36, and at 35 milliseconds, it was about minus 8.88. But then, as we switched, this thing jumped to minus 13.32. Plugging in here t equals 35 milliseconds, you get e to the 0, which is 1, so minus 13.32, and then get the case back to 0 in about 83 more milliseconds. And again, the total of that would be adding 83 to 35 milliseconds. That'd be 118 milliseconds. These switches could open and close again. You just follow the same 6-step procedure, again, with the same technique of evaluating the equation when you're finding your pre-switching conditions. And this is supplemental problem 511.